Okay, continuing the example from the previous problem, we're going to try and actually find the eigenvalues and eigenfunctions. You might want to skip this video because this is going to be exactly the same calculation, at least to start, as the heat equation. You might want to jump to the middle or the end, but I'm going to just go through and show all the details. X double prime plus lambda x equals 0, x of 0 equals 0, x of L equals 0. We're going to split this into cases based on lambda being positive, negative, or 0. Okay, case 1, lambda equals 0. We have m squared equals 0, which means capital X is c1 plus c2x. If we plug in our initial conditions, we get 0 is equal to c1 plus c2 times 0. That tells us c1 is 0. So plug in first boundary condition. Second boundary condition tells me 0 is equal to 0 plus c2 times L. That tells me that either L is 0 or c2 is 0. And same justification as the heat equation. We can't be plucking this string of a guitar with length 0. It doesn't make sense. So we're going to ignore the L equals 0 case and say c2 has to be 0. When these two things happen together, we're going to end up with a trivial solution. Not just because x is trivial, but because u, x times t, is also going to be 0. Okay, case 2 is when lambda is positive. You could put these in different orders. I'm just going to try and be consistent. We're going to end up with characteristic equation m squared is minus alpha squared, which means x is c1 cosine alpha x plus c2 sine alpha x. Again, be careful of your variables. Capital X depends on little x and so on. Let's see. We now have two boundary conditions. If you plug in time 0 and x is 0, the sine of 0 is 0, cosine of 0 is 1, so this tells me c1 is equal to 0. If I plug in the other boundary condition, 0 is equal to c1, which is 0, cosine of alpha L plus c2, which I don't know yet, times sine of alpha L. And again, if we have a product of two things equals 0, then either the c2 is 0 or the sine is 0. If the sine is 0, then the angle has to be a multiple of pi. And so I guess that means that alpha is going to be n pi over L. We can't have, well, yep. Let's see. Also, something to point out, in this case, lambda is alpha squared. We're assuming that alpha is a positive number, so this is assuming that n is greater than or equal to 1, or n is greater than 0. C2 equals 0 is actually going to end up being the trivial case. So we always end up with a set of possibilities, and then we kind of rule them out one at a time. Okay, case 3 would be lambda is negative, which I'll write as negative square of a number. That's going to end up giving us m squared is a positive square, and so we get plus and minus alpha, so e to the alpha x and e to the minus alpha x. Plug in the boundary conditions, we get 0 is c1 e to 0 plus c2 e to the 0. c1 plus c2 is 0. c2 is minus c1. If we plug in the other boundary condition, we get 0 is equal to c1 e to the alpha L minus c1 e to the minus alpha L. Again, c2 is minus c1. Factor of c1. And the only way for this to be 0 is if c1 is 0, or if the exponent is 0, in which case either alpha or L has to be 0. And then if you stare at these, none of these are actually realistic possibilities. C1 equals 0 would mean that this is a trivial case. U equals 0. It's not a real solution or not a helpful solution. Alpha equals 0 would mean we're secretly in case 1. Let's see, L equals 0 can't be because the problem has L as a positive number. I didn't write this in the problem, but the way I was describing it was that it was the length of a string or a rod. It doesn't make sense for that to be a rod of length 0. Okay, let's go ahead and solve the t equation at the same time. So t prime plus lambda a squared t equals 0. And this is the one place that's going to be slightly different than the heat equation. This is the first place that we're going to get a difference from the heat equation. We got as our eigenvalues, lambda was alpha squared, which means n squared pi squared over L squared, where n was positive. So that's the only value of lambda that makes sense. So when I see this lambda, really I could replace it with n squared pi squared over L squared. And if it mattered, I don't think it is going to matter yet, n would have to be a positive number. So our auxiliary equation, m squared plus n squared pi squared over L squared equals 0. M is minus this number, which means, m squared is minus this number, which means n is plus or minus n pi over L times an imaginary number. So t is going to be, let's see, I don't want to use C1 and C2, I'll use C3. Let's see, imaginary solutions, cosine n pi t, not x, over L, and C4 sine n pi t over L. Okay, so we have some eigenvalues and the corresponding eigenfunctions. So for this value of lambda, this is our t. So let's call these lambda n and tn. And let's go ahead and rewrite the xn. X back in case 2 where we actually had eigenfunctions and eigenvalues. X was given by, let's see, C1 is 0. And C2 sine of alpha x, and alpha is n pi over L. Okay, so those are the solutions of the two individual ordinary differential equations. You can also think about these as being the two eigenfunctions.